Hello everyone, I'm Sarita, Assistant Professor of Chemistry, Government Degree College for Women, Begumpet. I welcome you all to the session on UV visible spectroscopy. So in our last videos, we have seen what is spectroscopy, and we have also discussed about IR spectroscopy, the principle of IR, instrumentation part, and also its applications. Now, in today's class, let us discuss about another type of spectroscopy, that is UV visible spectroscopy. So in this class, what we will be discussing is, first, we will again discuss about the introduction of spectroscopy. Just a brief introduction it will be. Then principle involved in the UV spectroscopy, instrumentation, types of electronic transitions, the various terms which we use in this UV visible spectra, absorption and intensity shifts, and its applications. So, as we all know that spectroscopy is nothing but the study of interaction of the matter with light. So, whenever a light, that is which consists of electromagnetic radiations, when it interacts with the sample or a matter, how the matter undergoes change. That is what changes the light or the EMR will make in the interior of the matter or the sample. So the study of the interaction of matter with the light or EMR is known as spectroscopy. So we know that when the light falls on a matter, what happens to the light? It may actually, the matter may absorb the light and it transmits the light, or else the light which is striking on the surface of the matter, it can be reflected back. So this is the incident light. Incident light is the ray of the light which is falling on the matter. So some light can be absorbed and some light can be transmitted out, or it may undergo reflection. So all this happens when the light strikes on the surface of the sample or the matter. So this interaction, so this types of various types of that is absorption, transmission and reflection of the light, it depends upon the smoothness of the surface. That is smoothness of surface of the matter, the nature of the material. So what material the matter is made up of, and the angle of incidence. So what is the angle that the incident light is making with that of the matter surface? So these are the various incidents that happens when the light interacts with the matter. So as we know that the light is nothing but it is that is propagating in the form of a wave, and it is nothing but consists of discrete packages of energy which are called as photons. Now when this photon, it consists of both electric field and the magnetic field. These two fields will be perpendicular to each other. So the wave, this is the wave, light wave, which is traveling or which is propagating, and this wave consists of both the electrical field and the magnetic field. And these are what perpendicular to each other. So you can see this magnetic field, the purple color, and the electric field which is shown in the green color. So they will be always perpendicular to each other. Then there are some terms which are related for this light wave. The first is frequency. So what is frequency? The frequency is nothing but the number of waves that pass through a given point. And the unit of frequency is hertz. 1 hertz is equal to 1 cycle per second. So how many cycles, that is cycle is nothing but one complete wave per second, is counted as 1 hertz. Then wavelength. Wavelength is nothing but the distance between two nearest crusts or troughs. Now you can see this is the waveform of the light. So it is having the crust, we call this as crust, and it goes down, this is trough. So crest and trough. Now wavelength is the distance between these two crests, or we can also take the distance between these two troughs. And the wavelength is measured in centimeter, nanometers, or angstroms. Then what is amplitude? Amplitude is nothing but the height of the crest or the depth of the trough. So more the amplitude means more is the intensity of the beam of light. Then what is wave number? Wave number is nothing but the inverse of wavelength. Wave number is nothing but 1 by lambda. Wave number is represented by nu bar. It is nu bar, okay, and it is expressed as centimeter inverse or meter inverse. Then what is velocity? Velocity of a light is nothing but it gives the relation between the wavelength and the frequency. So C is equal to nu lambda. Nu is the frequency of the light and lambda is the wavelength. Then the energy of EMR radiation. So energy is given because as these light travels in a quantum known as photon, they will carry some energy. And that energy can be calculated by the formula E is equal to h nu. H stands for the Planck's constant and nu is the frequency. So how to calculate frequency? Already we have seen C is equal to nu lambda. Now from this, nu will be equal to C by lambda. So if we substitute nu value here, the expression becomes hc by lambda. So E is equal to h nu, or we can write it as hc by lambda. Then as I said, electromagnetic radiations, they are nothing but they are having the various rays in it. And all those are nothing but it gives rise to an electromagnetic spectrum. So gamma rays, X-rays, UV, visible, IR, microwaves and radio waves. So these are the various waves which are present in electromagnetic spectrum. And these gamma rays are highly energetic rays. And as we move from left to right, that is towards the radio waves, the energy of radio waves will be less. And the wavelength of radio waves will be more because energy is inversely proportional to the wavelength. With the formula E is equal to hc by lambda, that is h nu by hc by lambda, where energy is inversely proportional to the wavelength. So radio waves are less energetic and they are having higher wavelength. Even they also have higher frequency because E is equal to h nu. E is directly proportional to the frequency. So radio waves are having, the frequency of this is less and energy is also less, whereas the wavelength is more when compared to all the other rays. So if we are studying only about a particular wavelength of light, how it is interacting with that sample, then we have different branches of spectroscopy, such as if UV visible light is striking onto the matter, then we call it as UV visible spectroscopy. If it is IR radiations that we are considering for the study, how they are interacting with the sample, then it is IR spectroscopy. So in that way, we have different types of spectroscopies. So this is the white light which is falling on a prism and then it is undergoing diffraction to give different colors, 7 colors, which we call it as VIBGYOR. That is violet, indigo, blue, green, yellow, orange and red. And all these colors are visible colors. That is which are visible to us. All these colors have different wavelengths also. So you can see the wavelength of red light is maximum, which is 620 to 780 nanometers. So red light has higher wavelength when compared to all other lights. Then what are the principles of spectroscopy? So as we know that when the molecule or the sample is absorbing the radiations, what is happening is we have different, that is the molecule. Suppose if we are taking the study of the interaction of electromagnetic radiations with that of the molecules, we call it as molecular spectroscopy. If we are considering the study of EMR with that of the atoms, we call it as atomic spectroscopy. Okay. And in this case, after the EMR radiations are absorbed, some of the radiations will be transmitted out. So we have to measure the intensity of that absorbed radiations, or we can measure the intensity of the emitted radiations. And then we can plot the graph by taking absorbed or emitted radiations on the y-axis, and on the x-axis we can take frequency or wavelength. So that is nothing but the spectrum what we get by the study of this EMR when it interacts with the sample. Now we can have an instrument to measure this absorbed radiations or emitted radiations, and that instrument is known as spectrophotometer. Then in the spectroscopy, that is when the light is absorbed by the sample, that study we call it as absorption spectroscopy. And if we study the intensity of the light which is emitted out, that is nothing but emission spectroscopy. So in a spectroscopy, we have two types, absorption spectroscopy and emission spectroscopy. Now in absorption spectroscopy, what happens is when the radiations are absorbed by the sample, the molecules which are at the ground state, they undergo excitation because they will be absorbing the energy from the light, and then they will undergo transitions to the higher energy level. So all this absorption spectroscopy involves the excitation of the electron from a lower to a higher level. And for this, we require, that is absorption, we require the radiations which are absorbed from the light. For example, we can take UV visible or IR spectroscopy. So in UV visible, 185 to 400 UV, and then visible is 400 to 800 nanometers, where that particular wavelength of light is absorbed by the sample, and then the electron will undergo excitation. Then the other type is emission spectroscopy, where in this we will be measuring the amount of the light emitted out. So when emission spectroscopy, when does it take place is when the light is interacting with the matter, the electron is absorbing the radiations and it is excited. Now after that electron has been excited, now it comes back to the ground state by releasing some energy. That is nothing but it is emitting some energy. So if we study that particular emission of energy, that comes under emission spectroscopy. So in emission spectroscopy, the excited electron returns to the ground state. So whatever the electron that has been excited by absorbing the radiation, now when it is returning to the ground state, so that study is nothing but emission spectroscopy. Now we can just look at this animation where it explains how the energy is being absorbed and then emitted out. So this is the wave where you can see electric and magnetic field which are more perpendicular to each other. Now this is a particle where the light is falling on it. So when it is falling, you can see the electron is being excited to the another energy level, higher energy level. So it is spectroscopy is nothing but the interaction of the light with the matter. Light is nothing but here electromagnetic radiation with that of the matter. That is nothing but spectroscopy. Now this interaction of electromagnetic waves with matter is of two types. It may be absorption or emission. Now what is absorption? As I said, now this is the electron which is in ground state. When it absorbs energy from the light, it is getting excited to the higher energy level. So that is nothing but absorption. Now what is emission? The excited electron which is there, it is coming back to the ground state. So where it is releasing some energy or the light. That is nothing but emission spectroscopy. So spectroscopy is mainly used to find out the internal structure of the matter or any molecule. And what are the advantages of spectroscopy is here it is less time consuming. Okay, within just less than minutes, and it has, that is, we can use very small amount of sample is required and cost effective in the long run. Actually, to purchase it, it is cost, but in the long run, it will be very cost effective for us. So now when the light is falling on the matter, as I said, excitations, and then from the excited state, the electrons will come back to the ground state. So all these, nothing but we can study when we know about the energy level diagram. So in all the molecules, we have different energy levels. They are electronic energy levels, vibrational energy levels, and rotational energy levels. Now, when the suppose if the electron is here in the ground state, when it is absorbing the energy, it is getting excited. Now, this excitation can take place in all these three energy levels. So it depends upon the energy of light, what it is, that is the energy of light with which the sample is being interacted. So in this, the energy levels, the difference between the energy levels is high when compared to vibrational and then the rotational. So you can see these small lines are rotational energy levels which are present between the vibrational energy levels. And these vibrational energy levels are present in the electronic energy levels. So here, the excitation can take place between the electronic energy levels. So from lowest energy level, that is from E0 to E1. So for this excitation between the energy levels, electronic energy levels, we require lot of energy because the energy difference between the electronic energy level is more. So when the sample is interacted with high energetic radiation, then only it can undergo excitation to the higher electronic energy level. So that is, suppose if the molecule is subjected to UV visible light. Okay, so when UV visible light is interacted with the matter or the sample, this type of transitions from lower electronic energy levels to the higher electronic energy levels takes place. So here the delta E value is 35 to 71 kilocalories per mole. So that is the amount of energy that is required for this type of transition between the electronic energy levels. Suppose if the sample is radiated with lesser energy radiations, then we can see only the transitions between the vibrational energy levels. So there won't be any transition in electronic energy level. So from V0 to V1, the transition takes place. So V0 means ground state vibrational energy level to V1, that means excited first stage vibrational energy level. Because the spacing between these energy levels is small, that is, it is 0.01 to 10 kilocalories per mole. So lesser energy radiations can induce that is the transitions between the vibrational energy levels only. For example, IR radiations will induce only the transitions which are taking place in the vibrational energy level. So these vibrational energy levels, in turn, they contains what? They contain rotational energy levels. So rotational energy levels are very discrete and they are quantized. The energy gap between these rotational energy level is very, very small, and less amount of energetic radiations which are having less energy can induce this transitions between rotational energy levels, such as if we take microwaves. Microwaves are less energetic, and when the sample is irradiated with microwaves, only the rotational energy levels, the transitions between rotational energy levels is seen. So you can see delta E of electronic is very high. So you can see this is one electronic level, the other E1. Then vibrational, so V0, this is V0 to V1. Rotational, R0 to R1. So these are all rotational transitions. This is vibrational transition, and these are electronic transitions, which requires high amount of radiations, high energetic radiations. So these transitions, again, we can just recall them. So depending upon these transitions, where the light is interacting with the matter, so these are the various energy levels. So as I said, this is electronic, the red colored, blue is vibrational, and the green are the rotational. So different wavelengths are required for undergoing these type of transitions. So in the electromagnetic spectrum, as it is having different wavelengths, so different wavelengths will induce different types of these excitations. So in this we have pure rotational, vibrational, rotational, and electronic band. So rotational spectra requires very less energy of radiations such as microwaves. So you can see only the rotations of in the molecule is seen, so which comprises only the rotational energy levels. So microwave spectra, the study is known as microwave spectra. Then for vibrational rotational, the energy required is more when compared to the microwave. So for example, IR radiations, so they can cause both rotation as well as the vibrations, the molecule. And that is why this IR spectroscopy is also known as vibrational rotational spectra. Then the third type is electronic band spectra, where again here high amount of high energetic radiations are required, such as UV visible. So UV visible, they can cause rotations, vibrations, as well as excitation from one electronic energy level to the another. And these vibrational energy levels are also having these rotational energy levels, which are more closer to each other, and that we observe as band. So that's why it is known as electronic band spectra. So UV visible spectroscopy is also known as electronic band spectroscopy. Then now we are actually we are starting to discuss the topic, which is UV visible spectroscopy. So what is UV visible spectroscopy? It is nothing but when UV visible light is irradiated onto the sample, what happens? There will be transitions from that is from ground state electronic energy level to the higher electronic energy level. So because of these transitions, the spectrometer, what it does, it will actually find out what is the intensity of the absorbed light, and then it will give result as UV visible spectra. So for this UV visible spectroscopy, we require UV radiations. So UV radiations, they extend from 10 nanometers to 40 nanometers, or else you can just remember it as 10 nanometers to 400 nanometers. And visible radiations range from 400 nanometers to 800 nanometers. So UV visible complete, that is together, we can that is say that the range of UV visible will be 200 nanometers to 800 nanometers. So the first part, that is 200 to 400 is for UV, then 400 to 800 nanometers is for visible radiation. Now in that we have near UV region, which is 200 to 400, then far UV region, that means below 200 nanometers, we call it as far UV region. And that far UV spectroscopy is studied under vacuum condition. And generally the common solvents that are used for preparing the sample is ethyl alcohol or hexane. So these, they do not actually interact with the study of UV spectroscopy. Now what happens here? As I said, the absorption UV visible radiation, it generally results the excitation of the electrons. And here we can have bonding electrons as well as non-bonding electrons. So first we'll look at the bonds or the molecular orbital. So in the molecular orbital, how a bond is formed when the molecular orbital of two atoms combine. Okay, so when they are combining with each other, a bond is formed. That bond may be a pi bond or a sigma bond. So when two atom orbitals combine, so we will be getting either a bonding molecular orbital or a anti-bonding molecular orbital. So always bonding molecular orbital, that means BMO. BMO is the short form of bonding molecular orbital, which will be at lower energy level, and anti-bonding molecular orbital will be at higher energy level. So when the molecular orbitals are combining, it will give rise to bonding molecular orbitals as well as anti-bonding molecular orbitals. So bonding molecular orbitals will be at lower energy level, anti-bonding molecular orbitals will be at higher energy level. So sigma bond or sigma orbital, the molecular orbital associated with single bonds in organic compounds. And what is pi orbital? The molecular orbital which is associated with parallel overlap of atomic p orbitals. And there are n electrons. N is non-bonding electrons. That means these electrons do not participate in bonding. So the electrons which do not participate in bonding, we call them as non-bonding electrons or n, small n. Now, as I said, when the UV visible radiations are hitting the sample, what is happening? Molecular transitions takes place. Now, these transitions can take place between the electronic energy level. And that's why UV visible spectroscopy is also known as electronic spectroscopy. Now here you can see this is the sigma orbital, which is bonding sigma orbital, and sigma star refers to the anti-bonding. So always sigma star, that is anti-bonding, will be at higher energy level when compared to the molecular bonding orbital. Similarly, pi orbital, this is pi orbital bonding. Pi star means anti-bonding. Pi orbital stands for pi star. Now these are the energy levels of sigma, pi. Then we also have non-bonding, so small n. Then we have anti-bonding pi star and sigma star. So when the molecular orbitals are overlapping, we have bonding orbitals as well as non-bonding orbitals and anti-bonding orbitals. So here you can see these two are bonding. So always bonding molecular energy levels will be at lower, that is they are at lower energy. Then comes non-bonding molecular orbital energy level. And after that, you can see we have anti-bonding, that is pi star and sigma star. So sigma star is at higher level when compared to pi star. Now, when the light is falling, UV visible radiation is falling on the sample, transition will take place. Now, the transition may take place from sigma to the sigma star. Okay, we call this transition as sigma to sigma star. The other one is pi to pi star, then N to sigma star, and N to pi star. So here, if you observe, always the transitions are taking place from either bonding or non-bonding to anti-bonding. Okay, so the transitions in the that is the transitions in UV visible spectroscopy takes place from bonding or non-bonding levels to the anti-bonding. It is not from bonding to non-bonding. There is no transition that is taking place from bonding to non-bonding. So always transitions occur from bonding or non-bonding energy levels to the anti-bonding energy levels. Then if we take an example of formaldehyde, which is CH2O, here you can see the different energy levels. This is formaldehyde, carbon, which is having sigma bond with one hydrogen, another sigma bond with other hydrogen, and between carbon and oxygen we have double bond. One is sigma bond and this red one is the pi bond. And this oxygen, this triangle shaped electrons are non-bonding electrons. So on oxygen there are two pairs of non-bonding electrons. That means they are not participating in bonding. Now here you can see the bonding and non-bonding energy levels. There are 3 sigma bonding orbitals and 1 non-bonding orbital. So sigma 1, sigma 2, sigma 3. All these are what? Sigma bonds. Okay. And the other one is, other level is nothing but the non-bonding orbital. Then we also have a pi bond. So when we have a pi bond, we will have pi as well as pi star. Okay, pi will be bonding, pi star is anti-bonding. And you can see pi, this is the pi bond where 2 electrons are there. So fill 2 electrons in that. And we also have non-bonding orbitals. Okay, so non-bonding electrons are present because it is oxygen here. There are 2 pairs of non-bonding electrons which are there. So this is the level of N. So there is pi star which is vacant. Now this is sigma bonding. Then we have pi bonding. This is N means non-bonding. Pi star is anti-bonding, and above pi star there will be sigma star, that is also anti-bonding. Now the transition can take place from either the bonding levels or from the non-bonding level to the that is anti-bonding energy level. Or we can say that the transitions occur from that is lower energy state to the higher excited state. That means we have a term which is known as HOMO, H-O-M-O. HOMO stands for highest occupied molecular orbital, and there is another term which is LUMO, L-U-M-O. LUMO stands for lowest unoccupied molecular orbital. So always when the sample is irradiated with UV light, the transitions takes place from HOMO to LUMO. So in this, which is HOMO? This is HOMO. Okay, highest occupied molecular orbital is HOMO, and this is lowest unoccupied molecular orbital. So transitions takes place from HOMO to LUMO, that you remember. Then when these transitions are taking place, we get singlet as well as triplet states. So here you can see the transitions from non-bonding to the pi star, that is anti-bonding is taking place. So the electron which is present at the N bond, that is non-bonding energy level, is excited onto the pi star. So when the excitation is taking place, you can see the electron, spin of the electron remains same. That is, spin of the electron is not changed. That means we call that state as a singlet state. Whereas when the transition is taking place, if the spin of the electron is reversed, then that leads to a triplet state. So you can see both the spin of the electrons is parallel to each other in triplet state. Whereas in singlet state, the spin of the electron, this electron is showing downward, whereas the spin of this electron is upward. So both the spins of these two electrons are opposite. So when, or you can define like, when the electron is getting excited without the change in its spin, it leads to singlet. If there is a change in the spin of the electron during excitation, that will lead to a triplet energy state. So in triplet energy state, the spin of the electron, both the electrons is in the same direction, either both will be upward or downward. Whereas in singlet, one electron direction will be up, the other one will be down. That means the spin of these two electrons will be opposite to each other. So in this diagram, one electron has been excited or promoted from N to pi star energy level. That is non-bonding to anti-bonding. So one is giving rise to singlet, the other is giving rise to a triplet. So during the excitation of the electrons from one energy level to the another energy level, either it may lead to a singlet energy state or a triplet energy state. That we will deal with, will continue in our next class. So till now we have seen the introduction of spectroscopy, that is all the terms which are involved in spectroscopy, and we have seen the principle behind UV visible. So what is happening in UV visible? When the UV visible light is irradiated onto the sample, what changes we observe in the molecule? The excitation between the electronic energy levels is seen. Okay, so that is the reason the UV visible spectroscopy is also called as electronic band spectroscopy. And we have seen the that is different transitions. So always the transitions takes place from HOMO to LUMO, that is highly occupied molecular orbital to lowest unoccupied molecular orbital. So when these transitions are taking place, either it will lead to a singlet state or a triplet state. So we will discuss this topic further in our next class. So hope you have understood the topic, what is about UV spectroscopy and what are the different types of titrations. So in our next class, we will see in detail all those different types of titrations with examples. So thank you for watching.